Okay. So welcome to Math 349, Operations of Order. This is lecture 6. I'm just trying to see why it's not full screen over here. Okay. Okay. And so what I want to do today is continue to talk about the matrix exponential applications. And this was all inspired by the question of trying to figure out when can we interchange the order of operations in matrices. So one of the things that I think is a great example of where order of operations matters is Rubik's cubes. And so I recently was down in Lanesville, so I had my most expensive cube on me. This is about $250. This is a 13 by 13 Rubik's cube. We could have done the rest of the sides. We stopped at just one because it is a little time consuming. Can everybody figure out what pattern this is? Yeah, be more specific. What's the name of this flag? Or close approximation of what flag? Which US flag? Right, what is that flag called? This is a liberal arts college. You're supposed to have wide knowledge. Betsy Ross. But it only has 12 stars, not 13. Why does it only have 12 stars? So how does the medium influence the art? Right, so could I do 13 stars in a symmetrical pattern on a Rubik's cube like this? No, I could put another star in the middle. So this is a nice example of how the medium influences the art. So I decided to downgrade Rhode Island. It took too long to ratify the Constitution. It does not deserve both a star and a stripe, and I don't care that this is being recorded for posterity. If you are familiar with Steve Jobs and Apple, so much of Apple was inspired by some classes he took as a liberal arts student on calligraphy and writing and different fonts, and that became extremely important. So again, part of this is you never know where things are going to surface later in life. So later in the semester, I will make sure everybody learns how to solve at least a 2x2 Rubik's Cube. It's a good skill to have, and it's a great example of how order of operations matter. If you do things, if everything commuted, the Rubik's Cube would be very trivial and easy to solve. Because it does not commute, it becomes actually quite interesting. All right, so I want to continue and talk about the matrix exponential. Let's first just review the standard exponential function. One of the nice things about doing the lectures like this is I can quickly go back and see, yes, we did prove last time that e to the x times e to the y is e to the x plus y. Initially, e to the x is an infinite sum, e to the y is another infinite sum, and their product is a third infinite sum. But it turns out that the infinite sum is the same as e to the x plus y. So it's a good notation. We should prove that the sum e to the x converges. So the claim, so theorem, for all x in C, e to the x converges. And so there are many proofs you can do. So e to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial. Let's let an be x to the n over n factorial. If we want to show something converges, you should have seen this either in a real analysis class if you've taken real analysis. If not, you should have hopefully seen this in multivariable calculus. If you've taken 151, they assume you've seen sequences in series. If you've taken 150, that's something that they do there. If you did not take either one of these, hopefully you saw this in high school. If you haven't, just email me. I'm happy to chat with you or to post some resources on convergence. We want to be able to justify things. So we need to know a little bit of analysis. So the easiest way to prove that something converges is the comparison test. If I can compare this to something that I know converges, and each term is smaller in absolute value than a non-negative sequence which converges, then it converges. The problem with the comparison test is it requires you to be intelligent. You need to look at things and know what's a good thing to compare it to. It's very similar to factoring polynomials. If I give you a polynomial, say I give you, x squared minus 7x plus 12. Can you factor that? Minus 4 minus 3. No, it's minus 3 and minus 4. Really, minus 4 and minus 3. Yes, either way is fine. How did you do that? Intuition. What if I gave you, x squared minus pi plus pi x plus the square root of 3? Can you factor that by intuition? What would you use? Which formula? Quadratic. So use the quadratic formula. So what's nice about the quadratic formula is it's guaranteed to work. The roots are just negative b plus or minus square root of b squared minus 4ac all over 2a. Once you remember that, or once you search for it online, you just substitute what a, b, and c are, and you have your roots. Is the level of thought high? No. Which would you rather do for the first one? Would you rather use the quadratic formula, or would you rather just look at this and see it's x minus 3, x minus 4? You'd much rather look at it. That's how I view the comparison test. If you happen to know a good series to compare it to, that's usually the fastest way to prove convergence. But you have to know what to compare it to. If you don't, we have a whole slew of tools that we have learned to prove that a sum converges. And these are basically just roll up your sleeves and do algebra. So does anybody remember a good test to do for something like this? Ratio test. And I think the ratio test is easier here than the root test. So if I want to do the ratio test, let rho equal the limit as n goes to infinity of an plus 1 over an. That would be the limit as n goes to infinity. So that'll be x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And so I'll do the algebra very slowly. We have x to the n plus 1 over x to the n. Then we have n factorial over n plus 1 factorial. All right, the x to the n plus 1 over x just becomes an absolute value of x. And what is n factorial divided by n plus 1 factorial? One over n plus 1. And so as n goes to infinity, what does this go to? So x is fixed, n goes to infinity. This just goes to 0. So as the absolute value, actually rho is negative, as rho is less than 1, converges. Okay. So this is the simplest way I know to prove that e to the x converges no matter what input we put in. Well, input is a little bit vague. No matter what complex number I put in, this works if x is real, this works if x is complex. We want to try putting in a matrix. And so we want to look at e to the a, we'll do t, because that's what we're going to see later. So this is going to be the sum, n goes from 0 to infinity. Let's just do at to the n over n factorial. Does this make sense? So how would you interpret the n equals 0 term? How would you interpret a to the 0? So whenever I'm asking you something and you don't know the answer, reduce to an earlier dimension. So rather than looking at a matrix, we can look at a number. How would you interpret x to the 0? 1. How would you interpret a to the 0? So what would 1 be for a matrix? The identity. So this should be the identity. Then we should have at, and then what should the next one be? Any thoughts?
What do you get? It's to the 1. You're doing at to the.
Well, we're looking at various choices of n. When n equals 0, we would get at to the 0 over 0 factorial plus at to the first over 1 factorial plus at to the second over 2 factorial. And how should we interpret at to the 0? Well, if we're looking back to the exponential, e to the x, we can write this as 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. We're just trying to see how can we generalize that. So how should we view at squared over 2 factorial? Any thoughts? Okay, so a times t squared. So maybe a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial plus dot, dot, dot. It's essential A is a square matrix. Else a to the n, not possible. So t is just a real number or complex number.
Oh, just a generalizer. Okay.
Yep. So again, this is the nice thing about having all the slides from previous stuff available. When we solved the differential equation from before, where was it? Right. So when we were trying to solve y prime equals a times y, we got the solution was y equals some constant e to the ax. And so that little a is becoming our matrix A. I'm just using t rather than x as the variable, but we could still use it. Doesn't really matter. And so if A is a square matrix, we can do A times A. An n by n matrix times an n by n matrix is an n by n matrix. But a 3 by 4 matrix times a 3 by 4 matrix, I can't do that. So it's essential that A is a square matrix. So the question is, do you think this sum converges? As we take higher and higher powers of our matrix, do you think that this is going to converge? So what we can do is let's let b sub n be a to the n. Okay. So this is going to be some matrix. It'll be, b n, let's say 1 1 dot dot dot, b n 1 n dot dot dot, b n n 1 dot dot dot, b n n n. Some matrix like that. And so just using some notation. Or rather than using the letter B, I guess I can keep using the letter A. Doesn't really matter. And just so we'll use the letter A. And so now, if I look at e to the AT, let's look at what's going to happen. The first entry is going to be 1 plus A1 11T plus A2 11T squared over 2 factorial plus dot dot dot. And all the way down to 1 plus A1 N1T plus A2 N1T squared over 2 factorial plus dot dot dot. I just have some matrix like this. Each power of A is still going to be an n by n matrix. And I just want to collect them and then just see. So I want to show that this converges. So if I have some control over how large these matrix elements are becoming, I should be okay. Why should I be okay if these are growing but not growing too rapidly? Why is it enough if the matrix elements grow but not too rapidly? Yeah, my denominator is growing really fast. My denominator is n factorial. This grows extremely rapidly. If n is 100, when you go from 100 to 101, you divide by a factor of 100. That's tremendous. You then go to 102, you divide by such another factor of 100. That's 4 orders of magnitude you've just picked up in the denominator. It's growing so rapidly that as long as these are not growing too quickly, then we should be okay and we should win by a comparison test. So the question is, how big can the matrix elements be? And part of this is, again, just trying to get in your mind, how do you think about mathematics so that we can write it up? So I've reduced the problem to, I want some control over how large a matrix can be. Matrix elements. What could make matrix elements smaller when you multiply a matrix, when you take higher and higher powers? What could cause things to become smaller? What must be true about the matrix elements? So if they're less than 1, then when you multiply them together, that could make them smaller. Good. So let's start putting down what could make them smaller. What could make things smaller? Good. So having elements less than 1 in absolute value. And that would include your zeros, especially. So I'm not going to give you credit twice. So you get credit once, though. So remember to email me. So what else could make things smaller? Not modulo. So somebody give me some non-zero numbers that are big. 100 and what else? 101. Can you give me now a column of this second matrix such that when I multiply it by 100 and 101, I get something very small in absolute value? Okay, but let's take the element. I'm going to make it harder for you. I want my elements to be larger than 1 in absolute value. What can I multiply for that first row so that when I hit it with 100 and 101, that what I'm going to get over here in the upper corner is going to be small in absolute value? Nope. Yeah, how small do you think you could make it in absolute value? At best 0. So is there something you could multiply it by and get 0? Yes. Yes, you could. And so if you do that, in fact, what you would get is this would just be 0. So all of a sudden, I could have matrix elements that are very large, and when I multiply, things can become very small. So the second thing that could make things small is what? Not 0, negative numbers. So all entries not of the same sign. It's good. We're trying to build some intuition. What is the worst possibility we could have to make things as large as possible? Whenever we have negative signs, if we're just using a matrix with real entries, negative signs give us the possibility of having some cancellation. So if I'm trying to think worst possible case, if everything is positive, then I can't have any cancellation. And you can extend this to complex numbers, or you can just say, we're already doing enough, Professor. We've never really raised a number to a matrix. Can we just keep everything real for today? Sure. I'm teaching complex analysis at 11. I can get my complex fix later today. Not a problem. So what matrix, if you had to guess, so conjecture. Let's say A is n by n, largest element is m, worst case for growth of, let's say a to the k, is what matrix? If I tell you the largest entry of A is m in absolute value, do you have any guess as to which matrix might be the worst in terms of going to grow the fastest? All m's, excellent. So if we have all m's, there's going to be no cancellation. Everything is as large as possible. This is the worst case. Can you write this as a simpler matrix or a scale of a simpler matrix. Yeah. And all of a sudden, this is not so bad to analyze. So now I just have a matrix of all ones, and I want to just keep computing higher and higher and higher powers. And so if I want to justify this matrix conversion, this matrix exponentiation, the first thing you have to do is you have to show something exists. Once you show something exists, then you can start to ask questions about its properties. And so we just have to show that as we start calculating these higher and higher powers of the matrix and then adding them all together, that this infinite sum is going to converge. Well, the way we show it converges is we look entry by entry by entry. We look at the 1, 1 entry, the 1, 2 entry, dot, 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 the 1, n entry, and so on until we get to the n by n entry. And for each one of these, we have a nice infinite sum. And as long as these numbers are not growing too rapidly, we're going to be fine because we're dividing by n factorial. We showed earlier today by using the ratio test that x to the n over n factorial converges for all x. So if we can show that there is some universal number b such that each of these entries is at most, the kth entry is at most b to the k, so b squared, b cubed, then by the argument before, we're done. So clearly that b should involve m, right? Because my matrix, my worst case matrix is going to have an m. When I square, I'm going to get an m squared. When I cube, I'm going to get an m cubed. So I know that my bound has to be at least like a b to the k, like an m to the k. And then I just have to figure out, well, what happens if I take the matrix of all ones and take higher and higher powers? This is almost the easiest, I think, multiplication I can give you. What's going to be true when you have the matrix of all ones times the matrix of all ones? So we have all ones times all ones. What should we get? Okay. Matrix of all n's. So it's going to be n dot 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 n dot 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 n dot 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 n. So that's going to just be n times the matrix of all ones. Right? So what if I had the matrix of all ones and I cube it? Well, this is the nice thing about being able to just cut and paste. In principle. And nobody commented about whether or not it took more time to do this than it would actually have taken to just draw it again. And then we would just multiply again. And I'll just erase the n. And so what would we get now? N squared. And so this is why I wanted to cut and paste, because I knew I would be using this a couple of times. And if we have the matrix of all ones twice, we have n. If we have it 3 times, we have n squared. What do you think is true if we have it k times? Yeah, k minus 1. How would you prove this? Yeah, inductively. So this would be n to the k minus 1 times the matrix of all ones. Right? But we also have that to include that power of m, because we pulled out that m, so each time we have it. So if we look at the matrix a to the nth power, that would be m to the k, n to the k minus 1, and then the matrix of all ones. So each entry is less than equal to mn to the k. Why am I doing mn to the k and not m to the k, n to the k minus 1? I mean, the bound is n to the k minus 1. I don't want to keep writing k minus 1. This bound is going to be more than enough. It's showing that each entry is at most some fixed number to the kth power. And that's all I need to then feed into over here and say, oh, this is going to be at most mn to the first. This is going to be at most mn to the second. This is going to be most mn to the third. So I'm going to get basically m times n times t. That's some fixed number. And that's enough to give me convergence. And so yields each entry is bounded by 1 plus mnt plus mnt squared over 2 factorial plus mnt cubed over 3 factorial plus dot dot dot. So converges for all t. It just makes the writing a little bit cleaner not to have to do the k minus 1. It makes no difference.
This doesn't include the actual matrix stuff. It's not just scaling.
Well, I'm just looking entry by entry. So each entry of the 1 plus at squared over 2 factorial plus dot 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 converges. And so we really can raise a number like E to a matrix. And the reason is we're using this infinite series definition for E. And all we're doing is we're doing a whole number of multiplications. I do not know how to do root 2 multiplications. If you want to go into finance, they sometimes talk about half derivatives and whatnot. Yeah, I don't do stuff like that. I do nice integer stuff. I'm a number theorist. Okay. I can take a matrix and raise it to the first power, to the second power, to the third power. And I can use this to define e to the ax or e to the at. And so we're not taking an arbitrary number to a matrix. We're taking e, we're using the exponential function, which is this infinite sum, which was initially defined only for real numbers. And it turns out this works for matrices as well. We have shown that e to the ax, e to the at makes sense. So let's go back and let's consider, what motivated all of this. I think we were saying, v of x was equal to v1x, v2x, and we wanted to solve v prime of x was a v of x. And what's your guess? In one dimension, we had y prime of x equals a y of x led to y of x was some constant times e to the ax. What would you guess is the solution here? What would you guess for v of x? So in one dimension, it was a constant times e to the little ax. Almost. Nope. Constant, right? We can multiply by 5 or 17 or 24601. And if I multiply v by 24601, it changes both sides by exactly the same amount. So I shouldn't have a unique answer. I should have a unique answer up to some multiplicative constant. Right? Because if you look at the equation, if I multiply everything in v by 5, then I multiply everything in v prime by 5. And so it's still going to solve the differential equation. So whenever you're looking at things, you always want to get a sense of how unique is the answer. This is why when we do differential equations, I have to give you one additional piece of information if I want things to be uniquely specified. I need to tell you where you are, for instance, at some point in time. And once I tell you that, then everything is known. So we have a conjecture that if v of x is e to the ax, then that's going to solve the differential equation. So let's consider, let's say v of x is some constant c times e to the ax. What should the derivative of v of x be? So what should the derivative of e to the ax be? So what are you saying? So how should I write it? Or how else could it be? Oh, sorry, that should not be a little a, that should be a big A. How else could we have written it? So C is a constant, so it doesn't matter which side we put C on because C is a constant. But A is a matrix. So it might not be A times e to the ax. What could it be? It could be e to the ax times A. Now, if it is C A e to the ax, this would then be C A v of x, and we're done. I'm sorry. It would just be, sorry. I would move the C over, and this would be A of C e to the ax, which is A v of x, because v of x is C times e to the ax. So if when we take the derivative, if I can pull the matrix out to the left, I can then move the C back over, and that's my vector v. And I would get, oh, v prime is just A times v. That's what we wanted. So if v prime of x equals this, then we're done. But maybe the A is on the other side. Do you think A and e to the ax commute? So we started earlier by asking, when do matrices commute? Here's an example of why we give a damn. You should always be able to answer that question about the math that you're doing. What is the reason we care about this? Years ago, one of my students was giving a talk on joint work he did with me at Small, and he gave three reasons as to why you should care about this project. And the third was because my advisor who was funding me cares. A perfectly valid reason, not as good as 1 and 2, which were why the mathematical community would care about this. So do you think the matrix A and e to the ax commute? So let's look and see what we would have. We would have A, we would have I plus ax plus a squared x squared over 2 factorial plus a cubed x cubed over 3 factorial plus dot dot dot. As I move A and I get A plus a squared x plus a cubed x squared over 2 factorial plus a to the 4th x cubed over 3 factorial plus dot dot dot. So I can write the first one as the identity times A with A on the right. How can I write the second term, a squared x? I'm trying to show that A commutes with this. XA, not XA squared.
X I A squared.
I'm sorry?
X times I A squared.
Nope. AXA. And how about the next term, a cubed x squared over 2 factorial? A squared x squared over 2 factorial times a. And so this would then just become I plus ax plus a squared x squared over 2 factorial plus dot 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 times a. The commute. So you have to just show that you can justify all this? Well, same argument as before, everything is going to be fine. There is a very easy subset of matrices that commute with the matrix A. Any polynomial in A. If you give me a polynomial and I evaluate the polynomial at my matrix A, that's going to commute with the matrix A. So A commutes with any polynomial combination of itself. A commutes with A, it commutes with A squared, it commutes with A cubed, it commutes with A to the fourth. It commutes with any linear combination of these. So this is a nice way to review some of the stuff you've seen from linear algebra. So we now know that A and e to the AX commute. So all we have to do is we have to justify that we can differentiate term by term. And so, again, one of the ways to go in this class is to work on the textbook, the order of operations. And if you're considering graduate school in either math or computer science, any related field, it's really good to become comfortable with these theoretical constructs. How do we prove all of this stuff rigorously? It is so easy to gloss things over and just assume you can do things. And so again, one of my goals is to try to point out things that have been done with you in previous classes, but maybe not fully rigorously. So for example, what is the derivative of a sum? Some of its derivatives. What about the derivative of three functions? So f plus g plus h prime would be the derivative. Also the sum. I'm going to wager good money that you never saw proof of this. I'm sorry? Yep. So here's the proof. And, it's painful just because it's a little time consuming. I want to take the derivative of the sum. Now, I know that if I have a sum of two functions, the derivative of the sum is the sum of the derivative. I have a derivative of three functions. How can I reduce this to something I already know? Yes. So how should I group things? Good. Yep. And we'll leave h off by itself. Now we have a sum of two things. So now this is f plus g prime plus h prime as derivative of a sum is sum of derivatives. And now this is f prime plus g prime plus h prime, ditto. And now that's just f prime plus g prime plus h prime. So this is the proof that the derivative of a sum is the sum of the derivatives. How would I get the derivative of a sum of four terms? Same thing. And so if I want to do this formally and make the people who teach real analysis happy, what word would I use to make this a formal proof? This is a proof by induction, right? So this is, I think, the second time today we're doing induction. So if you really wanted to do this formally, this would be a proof by induction. So what this shows is the derivative of a finite sum is the sum of the derivatives. What we wanted to do, however, was the derivative of an infinite sum. So one of the things I really want you to get out of this class is when you need to be careful. When is someone trying to slip something past you? Whenever there is an infinity at play, that's the danger sign. You've got to be careful about what's going on. If there's an infinity, there is a good chance that something tricky is happening and you have to be very careful. I think in the first week of the semester, we looked at a double sum where depending on which order you summed things, one way you got 0, one way you got -1. This was to show the Fubini theorem for multivariable calculus does not always hold, right? We have to be careful. So it is not always the case that the derivative of an infinite sum is the infinite sum of the derivatives. Out of curiosity, how many people, it's not a requirement for this course, but how many people have taken real analysis? Okay, so when you took real analysis, did you prove that if you have a series that converges absolutely, that you can differentiate term by term in the radius of convergence? Okay, so for now, I'm not going to prove that. Instead, what I'm going to do is I'm going to just give you at least one example of an infinite sum that you can differentiate term by term, because it's fun, it's simple, it's a nice way to build intuition. It's one of the easiest infinite sums to study. And I love taking special cases and building intuition from that. What's the easiest infinite sum you can think of to study that I will let you? I'm not going to let you study the sum of all zeros. Easiest infinite sum of x. What series? I'm sorry, but I need a function of x. An infinite sum of x's.
1 plus x squared plus x cubed.
1 plus x squared plus x cubed. What series is this? Geometric. So let's take the geometric series. 1 plus x squared plus x cubed plus dot dot dot. And this equals 1 over 1 minus x if the absolute value of x is less than 1. Is everybody comfortable with the proof of that? Did we do that in class? Yes? Okay. So now, here's something that's really nice. So let's let s of x be 1 plus x squared plus dot 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 plus x to the n plus x to the n plus 1 plus x to the n plus 2. I'm running out of time, so we'll just do it like that. What can I factor out of all the terms there? X to the n. So this is going to be plus x to the n, 1 plus x squared plus dot dot dot. What can you tell me about the blue sum? Yeah, converges to 1 over 1 minus x. So if I have a geometric series, and I want to try to differentiate the geometric series term by term by term, what's nice is the tail of a geometric series is a geometric series. That's wonderful. It is very rare to have something like that. Who here has gone somewhat far in probability or statistics? All right, so I saw one hand. So you might have seen that a normal plus a normal is a normal. You know, it still keeps the same form. It's absolutely remarkable that if we look at the tail of a geometric series, we pull out the x to the n, and what's left over is another geometric series. And it's going to just give you back the 1 over 1 minus x. And so, you know, there are several ways we can go about, but now what we can do is we can now say s prime of x is going to be 0 plus 1 plus 2x plus dot 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 plus n x to the n minus 1 plus the derivative of x to the n over 1 minus x. How do we handle that? So this will be just, you know, the sum k goes from 0 to n of k x to the k minus 1. And how would we take the derivative of x to the n over 1 minus x? Quotient rule, right? We all remember the quotient rule. So we're going to get the derivative of x to the n, which is going to be n x to the n minus 1 times 1 minus x plus x to the n times 1 divided by 1 minus x squared. So if the absolute value of x is less than 1, as n goes to infinity, this goes to what? Less than 1 absolute value. As n gets very, very large, what does this go to? What happens to the denominator if x is fixed and n goes to infinity? Yeah, denominator doesn't change. Okay, let's look at the numerator. We have two terms. The second term, x to the n times 1. As n goes to infinity, if x is a fixed number less than 1 in absolute value, what does x to the n go to? 0. What about x to the n minus 1 times n times 1 minus x? Yeah, probably also 0. So the x to the n is going to be going to 0 exponentially fast and is going to infinity only linearly. So we just need to show, so this goes to 0. And once you show that, then this somehow became thick, right? This goes to the sum, k goes from 0 to infinity, of k x to the k minus 1, basically differentiating term by term. So if we can show that n x to the n minus 1 goes to 0, then we're in great shape. And so to do that, and I left myself one last page to do this, is consider the limit as n goes to infinity of n x to the n minus 1. This is 1 over x, the limit as n goes to infinity of n x to the n, where x is less than 1 in absolute value. So I could write x as maybe 1 over y, put an absolute value signs, with y greater than 1. So we have the limit as n goes to infinity of n over y to the n. How would you calculate that limit? Could use a comparison test. What would you compare this to? Well, but you can't compare it to 1 over y to the n because n is growing. So you know you've made it when your name becomes a verb. L'Hôpital. This is a job for L'Hôpital. It's a function of n. So this would be, if we just take the derivative, it would just be the limit as n goes to infinity of 1 over n y to the n, I'm sorry. So y to the n is e to the n natural log of y, right? So d by dn of y to the n is going to be the natural log of y times y to the n. And so that will go to 0. And so that finishes the proof. All right, so this finishes the section on matrix multiplication. When matrix multiplication commutes, there's a lot more you can do, but we saw a lot of really good concepts coming into play here. And I will send a little further note on this, and then we will shift to Fibonacci's on Friday.